I'll do what Simon said was the easy part. And it is true. What Felix just described is requires a lot of heavy lifting. But my goal here is now to talk about the statistical methods that we use to combine all this data once we have it. So I'll try to cover, I'll give a sort of brief review of what does meta-analysis mean in other settings, sort of in general medical research, and then the menu of options that we have to us for imaging. And I'll focus in and I'll zoom in on the methods that are used for coordinate-based meta-analysis before closing with some deep thoughts. So this, in some ways, recapitulates Felix's talk. So these are from another review article, "The Stages of a Traditional Meta-Analysis," and so it's really really what Felix was talking about. And so what? Oh no, the animation is different. Okay. Well, anyway. There are some check marks that are going down there to say that we can do all these. We would like to do all these, but it can be difficult to collect and validate these data rigorously. So I put a question mark next to 4 just to say it's not necessarily trivial to just stare at a list of coordinates and know are they good. As Jack was alluding to, you need to make maps, you need to make pictures and see are these coordinates falling outside of the brain. So that's a really important validation step. So not to say we don't do it, but just saying it's not as easy as it would be to do just by looking at a table. The other one that we really have a challenge on, and again, I'm sad it's not coming up, is number 5, display effects for each study with measures of precision. This is, again, from a review article on traditional meta-analyses. Well, unfortunately, when we just have the coordinates, that's not something we can really do, right? The coordinates are just the coordinates. There are no measures of standard error associated with those coordinates. They are just the coordinates from each study. Whereas if you're doing a research study, a meta-analysis on, say, drugs that lower blood pressure, you would get an estimate and a standard error, right, for each for the efficacy of each drug. So that's something that we can't do, and so and likewise we can't get necessarily measures of uncertainty in our maps. And I would say that while it's an area of work, we don't have many methods when it comes to this last item, publication bias and sensitivity analysis. So that's an area of I think of interest. So for non-imaging data, what are the standard methods? And the standard methods are, you may have heard of Fisher's or Stauffer's methods. We'll come back to this in a talk later to say more about it. They generally, they used to use this, the fixed effects model used to be standard, where it assumes that the only variation is the variation depicted in the standard error of each study. And then there is a random effects model approach where you say, well, additionally, I believe that each study is actually coming from a population, a slightly different population, and there is important study-to-study variation. And then finally, something else we don't really have a lot of in brain imaging is meta-regression as a term, if you've read the traditional meta-analysis literature, where you actually try to account for factors that might explain variation between studies. So for example, the year of publication, or sort of the subdomain in which this research was carried out. So let's start out with the most basic type of analysis in brain imaging, and that's an ROI analysis. So ideally, and it would be great if we had ROI analyses that were consistently reported across a large literature, we could do a traditional meta-analysis on it. And then we could take the mean, say, bold response and standard error. The problem is, in the world of brain mapping, we generally don't just look at one ROI. And you might say, well, some studies do report sort of what was the z-score, and maybe they'll have a percent bold change at a peak. But the problem is this is influenced by a problem called selection bias, or sometimes known as the voodoo correlation problem. That is, if you could basically scan all the subjects in the world and create a study with thousands and thousands of subjects, you would get this blue line here. But for your one study of only, say, 15 subjects, you're going to get a noisy version of this. And the peak of this is always going to be, in general, a lot larger than the true, perfect, noise-free version of that activation. So whenever you see a result that's reported in a paper that's based on a local maxima, which is by and large what is reported, that is going to be a biased estimate and not something suitable to enter into a meta-analysis. Unless you go see Sam's poster, who's actually trying to deal with this problem. It's my student. Sorry, I don't have the poster number there, of this selection bias problem. Okay, oh no, it's overwritten. There'll be a whole separate talk about how do we combine information when we do actually have the statistic images and what's known as intensity-based meta-analysis. Just quickly reviewing them here, we can use just the p-values or just the t-values or the z-values. We can use the original contrast data, or we can use them both. I'm going to skip through this because I'll say more about it in an upcoming talk. Just to say, if you read the traditional meta-analysis literature, they basically say never do this. Never just combine the z images because you're not using the full information. And what you really should be doing is this here. This is the standard thing to do in meta-analysis and for medical meta-analyses trials. But this is allowed to be done, but we just don't have this as an opportunity because in general, people do not share their image-based results. So unfortunately, there is not a lot of going on in intensity-based meta-analysis because the data is not available. But again, I'll come back to that in another talk. What I'll spend most of the rest of the talk on is coordinate-based meta-analysis. So given that we have things like the brain map database, and we have a literature full of papers that have tables of XYZ coordinates, this is the source of long-term data that we have to conduct meta-analyses on. So there is a pair of methods that have been implemented and are used rather extensively, ALE and MKD. They're based just on the coordinates, and as Felix alluded to, there's also a sign difference mapping method that uses the z-values additionally. I'm going to focus on the two methods that just use the XYZ coordinates alone. So both of those methods, in fact, all three of the methods are related, can be called kernel methods. They're taking the XYZ coordinates and basically replacing that infinitesimal dot, location if you will, with a kernel. They basically are taking the information, the locations from each study, convolving those locations with the kernel to make a map. So ideally, we would like to have the original statistic map that came out of the analysis software. We can't get that. This serves as our surrogate for that. So we get one of these maps per study, and then we combine them across studies and then try to do some sort of inference on this. And it turns out because this is a non-standard data, we cannot use a traditional general linear model. We have to use other techniques and other means to get p-values, and so we end up using Monte Carlo tests to do that. So let's dig in and look a little bit closer at the two different methods. So the ALE, the modified ALE method, works like this. So for each study, we place a kernel, a Gaussian kernel, at the location of a foci. And then this gives us, when we sort of combine those all together, we get a ALE per study map, and then these are combined to create a ALE map. And what's going on? The interpretation here should be that at any one location, this is the probability of observing a foci at that location. And how are these maps combined? They're combined with this probability combining rule, assuming independence of events, and that's how we combine these together. And so again, the precise interpretation is probability of observing one or more foci at a given location, conditional on assuming a particular full-type maximum. And the very first method that was proposed, the choice for this full-type maximum was kind of arbitrary, just sort of pick something reasonable. And so in follow-up work that Simon did, came up with a way to have a principal choice of the full-type maximum based on the study sample size. So that was one advance there. He also figured out a way to skip the Monte Carlo if you just want to get p-values for the intensity of these. Although if you want to do cluster inference on this map, you still have to do a resampling procedure. Okay, so now in contrast, the MKDA method, this is a kernel density analysis created by Tor Wager and colleagues, uses, instead of a Gaussian kernel, basically a boxcar or just a flat disk kernel. And so we get, for each study, we just add those up. And so the interpretation at any one point for one study is how many foci were within a given distance of this particular pixel or voxel. And then we combine those together to make an average. And this is now saying the average of, on average, across studies, how many foci were within a given pixel. The modified version of this, so as before, we have to choose this radius. And there was some concern that some studies, there's some variation between studies. Some studies will communicate many foci in a given region. Say for a given cluster, they might list all of the local maxima within the cluster. Other studies, in contrast, may only present one foci in a given cluster. So the ALE method has a way to deal with this, and in the MKDA method, the approach was to create this modified or multi-level kernel density analysis that does something very simple, which is to say, instead of computing what is the number of foci that are within a given radius r, you create basically an indicator map. You just truncate this at 1, and now you have an interpretation of how was there one or more foci within radius r. And so now you see we truncate this here, and the idea is that now this study here that happened to be quite profligate in reporting lots of foci will not overly influence the average study map. So this is the MKDA, and basically it's trying to make sure that we have sort of an even influence from each study. And there's other modifications to this. You can add weights based on sample size and what have you. And there's also a Monte Carlo test that respects the spatial structure of these points, so when doing the resampling. So this has got a nice, I feel, a nice simple interpretation that this MKDA map is not probability. It's just saying for any one location in the brain, what is the proportion of studies that had one or more foci within radius r? So that's a nice summary of all the studies that you're examining. Okay, so what are the limitations of this coordinate-based approach? Well, one of the challenges is effect size. So again, to go back to traditional clinical trial meta-analyses, it's all about getting an effect size with a measure of uncertainty, point estimate with a confidence interval. And there's no question about so the effect size. We'll say in MKDA it's a proportion, in ALE it's some sort of probability, but we don't have an equivalent notion of standard error or uncertainty. And the power is an issue, and this is something that Felix was alluding to. When you get lots and lots of studies, it can be the fact that your results are driven by a relatively small number of studies. And so it can be that, if you have 100 studies, you'll find something that's significant just based on 5. And I think that's one of the reasons, I guess you're sort of, maybe Felix was saying that 20 is a good number. Well, it is true. With 20, you will not get significance if only one study is showing it. And so that's some advantage. Now, one thing is that the traditional methods are what I would call sort of fixed effects as opposed to random effects. So what do I mean by that? So if I borrow a slide from my usual educational slides when I'm talking about fMRI, so now I'm not talking about location in the brain, but just saying a brain response. So if this x-axis here is now the percent bold change, when we talk about a fixed effects analysis, that's only considering the uncertainty within each subject. And when I say we want to make a random effects analysis, we want to make an inference that is relative to not just this relatively narrow precision, because remember, each subject in fMRI, there's usually hundreds, maybe 1,000 scans for each subject. So we actually have some pretty good precision about each subject's response magnitude. But what matters is the between subject variability, and that's an important aspect of a mixed effects or random effects analysis. It says, yeah, that's somewhat important, but what's really important is this subject-to-subject variability. So now, in the meta-analysis setting, we're worried about the sort of study-to-study variation. And in particular, is this an effect that's going to generalize to the population? So if I do a slight cheat here, I'm going to say, now this is actually an axis, the x-axis. This is actually space in an atlas space. We're basically asking the question, if these are all from the same region, what is the spatial uncertainty in that? And that's something that the different methods try to incorporate, but they don't have an explicit parameterization between study variance in a spatial domain. And so a small piece of self-promotion is that we have tried to attack this work in some statistical work I did with my colleagues in Michigan, where we actually did try to put a spatial model in it. It is a very complex Bayesian spatial model that is not necessarily easy to fit, but it does actually directly answer this question. It actually directly tells you what was the within-study variation, in particular if there are multiple foci, and what is the between-study spatial variation. So there's some work on that, but it's not something that's sort of easy to use routinely. The one thing we should be doing more with is sensitivity analysis, and there's some initial work on this. This is from a paper of Tor-Wegers. We're sort of indicating some methods you could take from traditional statistical analyses to see, you should ask things like this. Are the results being driven by a study that had the lowest N? I mean, that should give you pause if that's sort of what's happening. So there's some diagnostics that you can do to relate the effects and the pattern of the effects relative to the sample size. And here's an example of something that we might want to be suspicious of in this location. That most of the large sample size studies actually are not showing a response there, whereas the small ones are. So this would be an example of maybe we want to be, maybe that's an artifact, or maybe we don't want to trust that result as much as possible. And here's another example just that I worked up from just looking at in a region of interest. So for example, I just wanted to ask the question, if I'm just saying, let's say that if everyone used this threshold, so p less than 0.01 with no correction, and what if I were to, and I got this data from a meta-analysis of 154 studies of in the right amygdala. So the actual data are here in the diamonds. So what I'm writing are the proportion of studies that had one or more responses in the amygdala, in the right amygdala. And I get these triangles here because these are across studies, so I can actually get the standard error from simple binomial counting statistics. And so this is interesting. These are all the different counts, and here's the overall count. Okay, so about 30% of the studies showed a response in this. And you can say, well, is that different from 0? Yes. Woohoo. Yes. Okay, there's definitely something there. But you might actually ask, well, what if every one of those studies just did P01 uncorrected? Well, then by chance, you would find a response in the right amygdala sometimes. And you can work out that if you were using a whole brain FWE threshold, then actually you should get none. So that's saying, oh, that's good. So this is very different from where you should not get anything. But if you're using a P less than 0.01 uncorrected in every single study, actually you would expect more responses. So this is just relating to what you might actually see due to chance under 3 different ways of controlling multiple testing relative to actually what was observed here. And so it's another way we can sort of look at the robustness of the results. This is, again, another sort of shameless self-promotion, but just to look at this question, which I think is interesting, and that's a file drawer. You may have heard of the file drawer problem in traditional clinical trial meta-analyses. That's the question of, are the results that where a trial was started, but the result was negative, and so it could not get published, or the investigators did not seek to publish it. And there are statistical techniques to sniff out and detect such things. So working with the brain map database, we asked us another question, which is a similar related question. Here are the frequency of foci per contrast from the brain map database. So you can see many papers actually only have 1 foci per contrast. Then it falls down in a pretty smooth distribution. But if we believe that the points arise as per a random process, there actually is a law. There's basically statistical distributions that tell us how should this behave. And in particular, those statistical distributions will make a prediction about the frequency of 0 count images. I mean, negative images, right? There's 0 foci in them. And so we actually found that there's some evidence that if you believe in this whole sort of statistical framework, it suggests that for every 10 studies that you see in the literature, it's predicted there's at least 1 negative contrast out there that is not included. So we have an archive paper on this, and we're currently trying to get that into publication. All right, so I guess I'll stop there. So I quickly reviewed the IBMA techniques, and there'll be another talk on that later. And I also quickly reviewed the statistical techniques we have for combining maps where we only have the coordinate data available. And so I'll stop there.